All right. Hi. My name is Roland Bock. I'm head of development at PPro Financial Limited. It's a company for payment processing and for prepaid credit card programs. And I want to talk to you about a library that I wrote and that we are using heavily in our company. It's called Sqlpp11, and it's an embedded domain-specific language for SQL in C++. And the first question that most people ask when they hear about this, and they haven't heard about this from somebody else who maybe explained it already, is why on earth do we need just another SQL library for C++? And one of the reasons is this quote from Scott Myers from one of the effective C++ books, the second edition. It says, prefer compile time and link time errors to runtime errors. And I truly believe in this statement as a good guideline. So let's first take a look at what happens in those usual SQL libraries. Now, in usual SQL libraries, everything is done in strings. This is an example from Sqlpp11. I'm not using this example I'm not using Sqlpp11 as a bad example. It's just a common example. And they have good example code. And it's easy to use. I just downloaded this library, I compiled the example codes, just worked. So this is a good example in that manner. And what you can see, I'm not sure, oops. What you can see is that we create a table here with a string. So we send a string to some SQL object and then say execute. So that is creating a table. Then we create a statement. And statements are filled with, again, some SQL object that gets feed in a string. And then this is an insert statement, obviously, some columns and then some values. The values, we want to use real values. So we use some question marks to mark parameters. And then we stream in these parameters and execute the statement, right? Then afterwards, it turns out that this statement is a prepared statement. And we can just bind new values to it. That's pretty much the same as this streaming values into it. Execute it again, and we could repeat this several times. So now we have inserted several values into the database. And then we want to select something from it. So again, a string with some columns that we want to select from tests, some where condition, again with parameters, we stream something in. And then we tell it, OK, this is now something special. It's not just an insert or update or something which returns an integer. It's something that returns a row. And then we can analyze this row. You can see if it's empty, and then we can get values from it. OK, that seems easy enough. And it is used in so many projects, right? But who sees bugs in this code? Right, I see a few hands. OK. Plural, I use plural. So who sees more than 2? OK, still a few. More than 5, maybe? Right, 1. OK, that's good. OK, there are about 10 in here. Depends on how you count and how you resolve the problems. But let's start with the oops. God. New to this thing here. So the insert statement uses a column that's not even in the table. Then we have four columns here, but 6 question marks for parameters. So we are trying to insert 6 values into 4 columns. That's not going to work. Then we have 3 values that we stream in. So that doesn't match both columns, and and the question marks, so that's definitely wrong. Then it turns out that if you read the documentation, that you have to reset the statement after using it. So before piping new values into it, you have to reset it. So this whole stuff here is all complete nonsense. Then again, the number of parameters doesn't really match. Then you have a syntax error here in the where statement. Okay, then the number of parameters again is wrong. This name here is wrong, so we make a lookup by name. That is wrong. The 3 is wrong because of, well, we have 3 parameters here, but obviously this is C++, so it will start with the first index is 0, so 3 doesn't even exist, same with the on. And there is a good chance that these int and double are also wrong because, well, you can write anything there. The library will accept it, but, well, we don't really know what was meant with these select things here. All right, so that's bad. Now, I accidentally scrolled to the next page several times, so when I ask how many compile error messages you will get, or you saw the answer, you get no compile errors for this, because this compiles just fine. It's all strings, right? And then when you run it, well, you get something very useful like this. Error near in. Now, if you go back, well, it's easy to find, especially now that you know all the errors. Okay, this in, yeah, well, it's wrong, right? But suppose your code is a little bit bigger, let's say a few 100,000 lines of code in, I don't know how many files, then this is not very helpful. It would be nice to have at least a file name and a line number, something like that, okay? But as it is, you have to compile, have no errors, you run into an error, and then you search, and then you fix, and then you repeat the whole thing, okay? And this is quite weird because SQL is a structured language, and well, actually the S in SQL stands for structured, and it has strong types. And C++ compilers are very good at structures code and very good with types. So why can't we do it in a better way? But what we do is, in these libraries is, well, we have all this knowledge. We know our tables, we know our columns, we know the types of the columns, we know what kind of expression we're writing. We know that when we look at something and we are comparing apples and oranges, that this is wrong because we have all this knowledge. But what we do is we put everything in strings, character by character. We throw away all this useful information and give the compiler nothing to work with. Right? It's all just flat, one byte more boring as the other. Right? And then when you're finally done testing, somebody says, all right, now let's go to another database because it was so much fun testing all this stuff. And different databases have slightly different understanding of SQL, or they might not support those special features that you just used with the old database, right? So you have to test again, just go through all this nonsense once more, right? And when I first started to use SQL in C++, I thought, well, I used one of these libraries because that's the only thing that was available. And I thought, well, that can't be. And that was in 2008, and ever since then, I tried to come up with a reasonable library that does give me more feedback and more control over what I'm doing. Because as probably everyone here, SQL seems to be so simple, and you don't concentrate when you write the SQL code in C++ because you have all these important things to think about, and that's why you do so many errors, or at least I do so many errors when I'm writing SQL. And I don't want this. So I tried a lot of things, and over the years, developed libraries, several kinds. We used several generations of that in our company, and ever since C++11 was there with especially Verillic templates and auto. There's a new library that I've written. It's called Sqlpp11. And it offers an embedded domain-specific language to write SQL in C++. And it's, for everyone who was in the previous talk here, it is expression templates over and over again. For one of those uses which were not contradicted in this talk is for ease of use, right? So it does use compile time expression to give you a maximum of compile time control. There are other libraries. I know of at least one which also gives you an embedded domain-specific language for SQL. It's called Quince, or Quincy maybe. Stands for queries in C++ expressions. That does more things at runtime than Sqlpp11. This library here gives you the maximum control over what you might be doing wrong. Okay, now let's take a look at this, how it looks like. So this is a very simple statement, and I think everybody should be able to use to read that. So we have some objects representing tables. And we're going to use these tables in all the examples. So we have a person table and a feature table. It doesn't really matter what the columns are, but at least the feature table has a name and a column called fatal. And well, the feature loves C++ is obviously not fatal. And well, this is now the insert statement. So we insert into a table setting these values. All right. Who sees a bug?
You're actually inserting into tab person instead of feature.
Right. Okay. I repeat that. The table is inconsistent with the columns that I'm using. So here we have person. There we have feature. That won't fit, right? And so I'm doing stupid mistakes just for demonstration purposes, because we are doing all kinds of stupid mistakes also in the string-based libraries. I've shown you a couple. Hard to find, but with this library, well, the first thing that it does is it says, well, at least one insert assignment requires a table which is otherwise not known in the statement. That is exactly it. One of these insert assignments, at least one of these. So this one, for instance, uses a table feature which is otherwise not known in the statement. And this into thing is the one thing that brings tables to be known into the statement. So that is a very concrete message. And this is also, by the way, the full message, because in Sqlpp11, although there is a wonderful template stack, and the types that you might see here will go right straight through a wall in some cases. So if you have a little bit more complex queries, it could be really long, but the number of lines should be really, really small. So this is the whole error that you get, and gives you obviously gives you a file number or file name and a line number, so everything's cool, right? Okay. This is a select example. So we select all columns of P from P where ID is greater than 7 and the name starts with Jens. And then we can just, this gives you back a range that we can iterate over, okay? Range-based for. We have rows, and these rows are actually structs which are constructed at compile time. The rows contain members of those, with the name of those columns that we've selected here, and the appropriate type. And this is shown on the next slide in the error messages. So when I'm doing something wrong here in evaluating the results, similar to what we've seen in the string-based things, then the compiler again will tell us. It will tell us, in this case, that, oops, I misspelled name here. And feature is not a string. There's no viable conversation from this feature here, which happens to be an integer to string. This is the complete message that you get from the library, and then the compiler drones on for a few lines that you could construct strings with all kinds of data. So you will get, I don't know, 10 lines in addition. But it's very, very short, so it takes also care of this, these kinds of errors. Then an example to show off a little bit, because the previous examples were so short, and just to make sure that you don't have the impression that the library only supports very easy statements. So what we're doing here is we define a select. So this is a select, selecting two columns, ID and name from the person, and then we try to select the ID from feature as well. This is, if we would just write it like this, only the FID, then the compiler would tell us, oh, well, you have a name clash here. You have to make sure that the names are unique. So what we do is, similar as in normal SQL, we say, okay, we select f.id as some name. This name is defined above here in some macro that does something to make this work. All right, then, all right, from several tables, then some condition with a subselect in here, then group by having just to show that they are there. And then we give the whole thing, this select, a name again. So we say, okay, this whole select as X. And then we can use this, this object here as a table, just like as you know it, hopefully, if you know enough SQL, you can use selects with a name as a pseudo table in from. So we can join the person table with this select here on feature equals X cheesecake, right? And this is which is kind of cool. So we gave this select here and a column that we want to select with a special name, and this happens to work. It's now a member of this pseudo table. And then we select columns again. We would have name clashes again if we didn't pay attention to this, but the compiler again, of course, would tell us. So we select ID and name, and then we want to select all columns of X. Now X has ID, name again, so that will be name clashes. So what we do is something that cannot be done in normal SQL, but can be done in this library as a convenience feature, is that we take this whole group of columns and give this group a name. Okay. Right. And then when we take a look at the row, now the row has an ID, a name, and then it contains an element called X. That's this group here, and group then has name and cheesecake. Okay. Again, just showing off and showing that this name stuff, for instance, works pretty well and is not bound to very, very simple queries. All right. We have here is a different kind of example, because everything that we've seen so far is working only with statements where we know the complete structure at compile time. That is not always the case. Sometimes, I don't know, if you have a search interface, for instance, for some data structure, you may want to select certain columns only under certain conditions, and that is exactly what's happening here. This is what these so-called dynamic statements are for. So we do a dynamic select, say, oh wait, we want to select the column always, it's always from P, and then we will have some where condition. And then if this condition here is true, we add a new column, and if some other condition is true, then we add some where clause, so we can do this as well. But if we do that, obviously some of that name and type magic that we did before won't work anymore, because some of these decisions are made at runtime. So since this is statically defined as one of the columns for this statement, we can still access the name object in the row. That's no problem. But this feature is only added at runtime. So we have to go back to the same approach that the string-based libraries have. Well, we have to look it up via a string, for instance, or we could use an index, or I don't know. Okay. Right, and then since all of these queries that we've shown so far are statements that are directly executed, this one is a prepared statement that also is different in usage and much less prone to errors than what you have in the string-based case. In this case, we have a prepared insert. So we prepare an insert statement, and we say, all right, we always want to set this name and this feature, but with parameters. And what we don't do is we don't use just question mark or something like that, some unnamed things, some anonymous thing. We say, all right, we give this thing a name, in this case by just using a column called name, and a type. In this case, again, the type of this column. You could also provide name and column argument, name and type arguments as 2 arguments, but in this case, it just fits just well. We use a name and the feature column, which just happen to have the right names and types. And then this prepared statement that we just created, this PI here, that has an object called, a member object called params. And that again has objects of the correct name and type, so that, for instance, if we tried to assign an integer to this name, the compiler again would say, no, this is wrong. So most of the mistakes that I showed on this first slide, pretty much, yeah, well, all the mistakes that are shown on the first slide are caught by the compiler due to the nature of these expressions, except for these very, very few exceptions that you have when for instance, you select columns dynamically. Then, well, the compiler can't help you. But it will help you with the overall structure, right? And with the expressions that you add there. And it will help you and say, for instance, if you try to dynamically add another column called name, it will tell you, well, we already have a name, please do something else. So even in the dynamic case, it will give you a lot of support. All right. Yeah, this is another mini quiz. So we select all columns of T from T and do an outer join with F on some T alpha equals F omega. So that's going to be interesting. Or let's say, who sees a potential bug? Right? Okay. Any of you uses Sqlite? All right. So in that case, Sqlite doesn't support outer join. And the library will tell you, well, okay, if you're compiling this and using Sqlite, the library will tell you that, hey, this won't work at compile time. You don't have to wait until runtime. It will tell you at compile time that, hey, this is not going to work because Sqlite doesn't support outer join or right outer join. Anyway, both. And again, this is the whole error message. Okay. So errors can be vendor specific. Also, features in SQL can be vendor specific, right? So this is another SQLite example. So SQLite has this insert or replace into, which is not part of the Sql11 library because, I mean, that library cannot in any sane way cover all databases. But it can be extended with this Sqlpp SQLite3 namespace and a function that does exactly that. And then it behaves just like you want it to behave, and you can have all the type checking and all the name checking and logic checking, whether you're using the correct tables with the correct columns and so on. You can have all that also for your very specific things. Okay. Right, so as an intermediate summary, Sql11 offers you an embedded domain-specific language for SQL and C++. That's very helpful in doing all those validity checks to make sure that your statements, even whether it's full statements or partial statements, that they make sense in the context that you're working with. And it can even handle those vendor-specific features at compile time, right? Now, any questions on the usage? Because, I mean, we're going to get to how this works or how parts of this work. Can explain the whole library, of course, but any questions regarding the usage of this library?
How do you generate these types which are used as tables, for example?
Okay, yeah, okay, I'm going to get to that.
Is there an abstraction so that you can change the SQL implementation at runtimes? For example, if you develop an open source application, I'm here, by the way. Here.
Sorry,
here.
Can you repeat that?
Hello?
Yeah.
Can you change the SQL implementation at runtime? So, for example, you develop an open source application that gets packaged by some Linux distribution, and they decide that, well, our users can decide whether they want Postgres, MySQL, Maria, SQLite, whatever. So, is there like a common layer beneath that can be used that then checks at runtime whatever it dispatches to? Still with static analysis?
In theory, yes. Currently, no, but in theory, yes. So if anybody's interested in that, personally, I currently have no use for that, so I won't write that part, but in theory, yes, you would. Well, and then it depends on how you implement it, whether you can use vendor-specific features, yes or no, whether you want to reject everything that is vendor-specific at compile time, or whether you want to say that, okay, certain parts of the library are not going to work, or whether you are going to do workarounds, it depends. But you could, and I'm going to show you very, very few things about how to interact with databases and do specific things.
Is it still possible to specify the full where statement as a string? So with losing the compile time checks, of course, but having the whole full where statement as a string?
Okay, so the question is if you could define parts of the query as strings, right?
Yes.
All right, yes, that's possible.
Great.
And it's very important because if that part of the language is not implemented as expression templates yet, then you couldn't work with the library if you wanted to use that feature. Okay. Okay.
Is it possible to get the resulting SQL code of the expression language?
Okay, so the question was if you can get the resulting SQL code of the statement. Yes. Yes, you can. So there is a serialization method to do that.
And the second question, is it possible to work with multiple connections? I haven't seen how the connection is used, but for bulk load, maybe it's important.
What do you mean working with multiple connections? I mean, this DB object that I'm using here all the time represents one connection. You could have multiple of those, obviously. You could do some pooling if you wanted. That's basically up to that partner library that I will just come to on the next slide. That does actually do the connection to the underlying database.
Okay, the DB object is with one connection initialized.
Yes. Okay, sorry, that wasn't heard by everybody. So the database object represents one connection. Okay. So some of these questions were targeted basically to this slide. So if you're using Sqlpp11, your code is going to have these layers here. So you have your user code. That is the stuff that I've just shown you. So these expressions and evaluating results and so on. That is interacting heavily with the Sqlpp11 library, which is vendor neutral. It doesn't know anything about any database. It knows quite a lot about SQL, but it does have no knowledge whatsoever about any vendor, doesn't know MySQL, doesn't know PostgreSQL, it doesn't know database, Microsoft database servers, nothing. But it has partner libraries. I call these Sqlpp11 connectors. These connector libraries provide, on the one hand, the glue code between the Sqlpp11 vendor neutral thing and the database. So, for instance, they translate the expression that you generated into a string that is understood by the database. On the other hand, these libraries can provide extensions to the core library and, for instance, offer this insert or replace feature like that we have seen here in one of these examples. They can also say whether some feature is not supported by this library. Right, and then of course you have the native database. Right. So one of the core things in this library is names. So you have names for columns, and these names get somehow transferred into the result row objects. They are used for parameters. You can use aliases and rename things. So that is one of the core questions that I get when we talk about this library. How do names work? And the idea is very simple. It starts with this template. I call it the member template. Cannot get much simpler. So it's a template. It's a template with one type as a parameter. It has one member. This member has a specific name. That is important. In this case, the name of the member is feature. And the type of the member is, of course, the type that you give as a parameter to this template. Now, how do you use that? Well, you can use it like this. You inherit from an instance of this template. What you now have is that my struct has a member which is called feature, and in this case has a type int. Okay, everybody following? Okay. Right, now we come to the, I think you asked that, about how tables and columns are specified. We come to that part. And it's still about names, so don't worry. So what we see here is a real-world specification of a column. Oh, and a typo. So what we see is, let's start on the bottom. We see that this column has certain traits. It's an integer value. It is required if you do an insert statement. This is one of those values that you have to provide. So in addition to the SQL language by this library that you can use if you want to. It has some name stuff above here, so it turns a string literal into a character sequence, so that later on in the library we can compare names and assert uniqueness of names. So everything that has the name feature also has the same character sequence for these letters here. And later on we can compare types because, and this is used because in the C++ compiler, it's always easy to compare types. It's much harder at runtime, compile time, sorry, to compare strings. Much harder. So do it once, turn it into a type. That's it. And then we have this. Sorry. Then we have the member template that we've just seen. And for the column feature, just looks like this and has some, for metaprogramming, nice call operators which just return this member. If you don't know the name, this is good. Okay. Before I forget that, this code is something that you should not write by hand, obviously, because it's very repetitive. You have to do this for every column. But in most cases, you will have a DDL for your database, or a description of what your tables and columns are, and it's very easy to use some, I don't know, Python script or something to translate this DDL into such code. That's very easy. If you really wanted to write something by hand, I probably would use a macro to do that, because I mean that is easy. It's easy to translate something like this into a macro. All right. Now, tables are similar in the body, so they again have this on the inside, this thing that turns a string literal into a type, and they again have this member template. So, well, you can use the name of this table anywhere, right? And then a table inherits from a table template using CRTP. So this is how this alias information gets into the table template, and then it uses the column specification for all the columns which are in this table as additional parameters. And then when you look at the table template, you now see how those column members get into the table. They get in there by multiple inheritance. So you have a variadic template. First is the CRTP argument, the table itself, and then come all the columns, right? And we inherit from, in the table, we inherit from a member template, right? So forget about all this here, but we inherit from a member template, and the type is a column template for this column specification. Okay. Make sense? More or less. But what this does is it brings in, for each column specification, it brings in one member of with an appropriate name, so the name of the column and the appropriate type into this table struct. Now for tables, it will be simple to write this thing if you have a code generator anyway. I mean, then this doesn't really make that much sense. But we're using this the same technique also for results, because now when we call the select statement, we use these column members. These column members get into a select statement. Yeah, variadic CRTP, by the way. But anyway, so this is one result field. A result field gets from the select statement for each column that is selected, one result field specification, this one here. this one, the field specification, which contains basically the information of the name and the type of the selected column, right? Uses that member template, again, to pull in appropriate members into this result field. In this case, only one. And the type is, well, the reasonable result type for the selected column, okay? And these result fields are then used in result rows, and here again we have multiple inheritance to bring in all the columns, or the field expressions, field representations for all columns into the result row. Okay. And just to round the topic names off, we've seen these calls to rename things. There are these with the function as something. The as something returns just a very, very simple template. It uses the expression that we want to rename as one argument and some alias provider which has such a name as arguments. And then it internally uses an alias type which then contains one of these member templates and the expression itself. So the whole thing contains whatever you gave it, right? The original expression, and it now has a new name because the name of whatever you use in Sqlpp11 is defined by this alias template. And the alias provider is it's also very simple if you more or less understood how these column and table specifications work. It looks just the same. It is a macro that you give a name, and then it creates a type that contains basically a member template for this name that you specified in the macro, and then generates some const expression value that you now can use as the name provider that we have just seen. Okay. Right. Now this whole thing could be so much easier because it's so much work, and I'm really annoyed by it, I have to say that. It works just fine. It works really beautifully, and I wouldn't want to live without the features that come with it. But it could be much easier if we could reason about names in the same way that we can reason about types and values at compile time. Sadly, we can't, but just if we could, and we could say something like this. So our member template would, instead of having a name that somebody had to type somewhere, that we could have a generic member template that we could instantiate with a name. That would be so much easier, right? I'm just dreaming here. I'm just saying it would be really, really great if a column specification could just look like this, right? That would be everything, instead of having a whole screen full of code. And this is bothering me so much, I really intend to do something about it, but I'm not going to be able to write a proposal on my own. So if anybody is interested in co-authoring or authoring them on their own, I don't care, please get in touch. I want this to be easier. All right. How much time? Okay. All right, so the second part is about how statements work. All right. Statements are, again, Veridic templates, and they're doing Veridic CRTP again. So what you're seeing here is the most important part, let's say, of a statement template. So a statement could be an insert or a select or an update, what have you. And it takes, we ignore this database parameter for a while. It takes a bunch of template parameters and inherits from base templates within these classes that we're giving here, and inserts basically inserts itself again as template parameters into this. And this looks horribly complicated. And it took some while to get there. But it can be used in a relatively simple way. And if you want to introduce special features into this EDSL, then this is one of the points where you can do it. So a select statement consists in the normal case of well, something that indicates that it's a select statement. Then it starts with an empty list of flags, such like all or distinct. Then there is no column list yet. There are no froms. There's no where, and so on. And when you call the select function, you just create one of these objects. Typically, if you already know what columns you want to select, these are going to be in the argument. So then you just add columns to the select statement. Right. So if you want to add special features, well, all you have to do is to, I don't know, remove some of these or add your own parts to it, right? So I don't know, if you have Oracle, you have this hierarchical from or hierarchical search. I'm not too familiar with that, but you would probably replace this generic from with something which is specific to Oracle. And the question, obviously, is how do these things look like? Because, I mean, it's easy to say it just replaces with what you need. How do they look like? And this is a bit simplified, of course. It's not that simple, but in a simplified way, it looks like this. So this is when we don't have a from yet in the statement. And as I've shown, we inherit from this base template within the class. And this thing has a from method. So when we inherit from the base class, then we inherit this from method into our statement. This from method takes a bunch of tables, does some static assert to make sure that this actually are tables, and some more static asserts to make sure that these are unique, and so on and so on. So does all the argument checking. And then it returns a new statement which, through some template magic, replaces the no from with now a from, because we have just added tables to it with a from call. So we replace the no from with a from. And the from is very simple. It has some from data in some class, whatever you want to name it. And the base T, so from the thing from which we inherit, just contains this from data, right? And if we're in the dynamic case, or if we have a dynamic from, then this will have the add function so that you can add additional tables to your from at runtime. Right. Yeah. Okay. So the next thing about things that you can put into statements is a serializer, obviously, because these elements in the statement have to be represented as strings for most database backends. Serializers are typically very simple. They are a specialization of some serializer template that takes a context that is something that is database specific, and then specialize, for instance, on the from data. And this static underscore method here is the important part that gets called in the course of serialization. And it just streams from into the context and then serializes the tuple with a comma separator. And that's it. Okay, so, and obviously this is another customization point for connector libraries. So if you want to do something specific for your database, well, you have several options here. You can, for instance, use a static assert here. I mean, probably not in the from, but if this were the outer join, you could use a static assert here and say, okay, I don't support outer join, right? I'm going to show better techniques than just using static assert tomorrow, but that's something that you could do. Another thing that you can do is you can specialize the way that something is serialized. So, for instance, string concatenation. String concatenation looks quite different from in MySQL compared to, I don't know, PostgreSQL or SQLite, because MySQL has the concat function where others have the concatenation operators. But this would be the place. You use your own, the context of your database as a parameter for the partial specialization and just do what is required for your database. And this way, well, somebody has to write the connector library and has to take care of all these special features. But once that's done, you will probably not run into database-specific problems. So migration is much less of a problem due to stuff like this. All right, so summary. Again, SQL11 offers an embedded domain-specific language for SQL. It does these partial and full statement checks at compile time. So it's much less likely that you have all those stupid errors that you typically have when you're coding SQL in C++. Just as an anecdote, on Tuesday I ran into an SQL error in my own code for the first time in 1.5 years. I'm doing lots of SQL programming. Was due to one bug in the library that is now fixed, so I won't have that again. SQL11 itself is vendor neutral. That is very important because it keeps the library in a controllable size, and you can use the connector libraries to do all the stuff that you want to do, like, I don't know, including connection pooling and including special behavior for certain features. You can do all that in the connector libraries, and there is very well encapsulated and isolated so that you don't create a mess. And of course, you could also use a connector library to work with several libraries. Then you have to think about what you want to do at those customization points, what you want to do with features which are not supported by certain libraries, how you want to handle that. I don't know. It's a matter of taste then. All right, so what's next? Well, SQL11 could be the foundation for type-safe SQL in general in C++. It could be used for quite a lot of things. Obviously, SQL databases. Also, I think quite obviously for ODBC database. There are people who want to use SQL for no SQL databases. Well, if they want, it would be easy to write a connector library for that. I'm not going to do that, but people could. There is an experimental version of an SQL library that works with vectors. Yeah, with vectors and lists. I think also with sets probably. You can currently do insert, update, and select. So you can use SQL statements in a similar way that you use it in LINQ and C#. You could use SQL statements on data structures. This is probably not going to be that cool until we get reflection into the standards. So it will take some time until people are really going to use it. But in the same way, you could use it on streams, You could today write libraries that use SQL on some XML or JSON, I don't know. So you're not limited to SQL databases, the main thing here. And you're not limited to using string-based output because you have an expression tree, and within this serializer object, you can do anything you want. You don't have to create a string. You can turn the current expression into a different expression. You can do SQL optimization if you want, and if you have a strategy for that. So there's no real limit. The statement expression is at your mercy. You can do whatever you want with it. All right, so acknowledgements. Thanks to everybody who uses the library, contributes to it, asks questions, listens to me when I talked about it, and spreads the word. And with that, thank you very much.
What backends are currently supported, or are any of them bundled with Sqlpp11, or do you have to go out somewhere else to get, like, how does that work?
They are not bundled. Currently, there are connector libraries for MySQL/MariaDB, for SQLite 3. There's a third-party implementation for PostgreSQL, and my experimental thing for STL containers. But just to give you an expression, to give you an impression, the connector library for SQLite was a one afternoon project to get it running, to do all the specialization. So, for instance, to support the insert or update thing, that is something in addition, but also like especially insert or update, that took, I don't know, 3 hours. It's not much work to do this. It's if you want to do something different than serializing to strings, then that's really different, and that's difficult. So this interface to standard containers, that already took, I don't know, 2 weeks or so, and it's not complete yet. So that's more complicated. But if you want to just connect to just a new database or do something specific with pooling or stuff which is not supported by the current, it's not much work.
First of all, thank you for this very impressive. Here.
Okay, cool. Thanks.
Thank you for this very impressive library. The first question: how is Microsoft Visual Studio supported? Because you're using a fairly advanced C++11, and have you any experience with Microsoft tools?
The last time I tried to compile, that's a very, very minor parts of the library, was a few weeks before CPPCon, so sometime in August. At that time, it failed with very, very, very core things in the library and very, very simple stuff. So I don't know, I'm using how do I say that? A static assert that uses an argument that only fires when it's instantiated, and this already broke.
Which compiler version did you test?
The latest experimental thing that they had out at that time. Okay. Whatever that's called, I don't know. I talked to several developers of Microsoft at CPPCon. They hope that during the year 2015 they will be able to compile stuff like this.
Okay. How is your experience with real-world performance on, well, I guess Clang and GCC with big tables, lots of tables, because I think the types you're generating, or your library is generating, are fairly huge. Mm-hmm. And we've been doing something which is similar. So we have built our own SQL, EDSL, but not so heavy weighted on the compile time side, because we had huge compile times and huge problems on the Microsoft platform.
The question is what you call huge compile times. I mean, of course, this library does so much more than string-based libraries, so it takes longer, that's for sure. But let's say all the queries or all the statements in this talk on my machine, that's a 4-year-old laptop, will compile in, I don't know, 3 to 5 seconds, something like that. So yes, it takes longer, but I think it's acceptable, because the amount of comfort that you gain with it is enormous. It really changes the way that you do database programming when you have all this compile time support. So I don't know what you call enormous compile times. I have, all right, to put it in a different context, I've tried to create one time a statement that is insanely huge, so it was, I mean, more than would fit on one of these screens. It doesn't take long. I don't know, a second maybe. Right?
I want to use this for spatial databases, so spatial queries, spatial columns. Do you? I know it's not yet supported, but what do you think is the effort to be able to support those kind of things?
What do you mean with special database?
Spatial geometry.
Oh, yeah. We actually had a discussion about this on Boost. So maybe you can read that up. So what you need to do in order to use a spatial database is, of course, you have to add new value types, new column types to, I don't know, for instance, for polygons. If you take a look at how integers and text values are implemented in the library, I think it will become clear very quickly how to implement polygons and stuff like that. I haven't really done that yet, but it shouldn't be that hard. I'm not saying it's a matter of 2 hours or so. It's probably a matter of 2 days, but I would be surprised if it's more.
I thought the main reason is to get compile time errors for your library. That's what, yeah. Okay, let's say my question, what's the advantage of Sqlpp11 compared to embedded SQL? With embedded SQL, I can write SQL. If I want to access a database, then I want to write my SQL code, and I don't want to write something else which could be SQL. I think this is this SQL code. Maybe it's something else, and I have to spend a lot of time to create my DDL to your library. So what's the advantage compared to embedded SQL? There I see if the type is wrong at compile time as well.
To be honest, I'm not too familiar with embedded SQL. So that is probably something that we could discuss offline, because then we could discuss pros and cons. I can't really comment on that now.
Do you have any support for stored procedures to generate directly from your code?
For stored procedures, not now, no.
And what is the flow? Let's say you have an application, you are connecting to the database, somehow you have to generate the structures mapped on those tables that exist into the database, and after that to get access to effective data. So you are doing this automatically. There is a point where I'm missing how are you matching the C++ types with the SQL types of the columns. Here, maybe you can try to explain a bit more. The mapping between.
The mapping, okay. Well, in all the projects that I know that are using this library, the mapping is done at compile time by some generator. So within your make process, you have a generator that generates code for this libraries that contains the column and table specifications based on that data definition of the database you're using. So if the databases that you're actually using in production get out of sync to what you used at compile time, then I'm not sure if that's what your question is, but
Somehow your database structure may change.
oh yeah.
By SQL manager, I don't know. In that moment, you need to recompile your application in order to map on new applications in your database.
Well, I mean, if your database definition changes in a way that affects your program, you will, regardless of what you're using, you will have to change something. And you will have to, well, probably you will have to recompile. But for using the full features of this library, you have to regenerate these table and column specifications and recompile and probably run into errors which tell you that, well, yeah, the name of the column changed and this code is not valid anymore.
Okay, thank you.
Got the sign that we have to finish this.
So time is over. I wish you a nice evening. We see us tomorrow.
Okay, thanks.